All right. Today we're going to start chapter 2, which is now we're going to deal with graphing and different ways of representing our data sets. The first one we're going to talk about are frequency distributions. We use that to organize and summarize our data. And you wonder, okay, now how's that? Remember we talked about yesterday that if you're doing a research study, the more data you have, the more information you have, the better your results are going to be. But the more you have, it means the more you have to process. Remember, data is simply numbers, inputs. You have to process them before they become information. A frequency distribution is a partition of classes by their frequencies of data, or the number of data in each class. We'll look what that means in a second. So our first thing we do for this chapter, we're going to use this data set. This data set represents daily commute times in minutes in LA. So these are the people who recorded. There are how many of them? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. 9 times 5 is 45, plus 5 is 50. The way we represent that in mathematics is, since we have a sample data here, we're going to say that n equals 50. N represents the number of data points you have in your data set. So that's what n represents. No, don't mix them up like that. Don't mix them up. They were stacked perfectly. No. Just take the top part. Just take the top stack. Yes. I hope it's not messed up. Okay, thank you. Yeah, so when you come in, just take whatever's on top. Don't major, because that now everything on the bottom is gonna be mixed up. Here's an important notification. Whenever you read these things, lowercase letters represent samples. Uppercase letters represent populations. A population. Because that way you'll know if it has a lowercase n, then you know that this number is an approximation. It's guessing the population. If it was a capital N, then we know that that's the entire population. So whatever I come up with in the calculations is the solid truth. So what can we do with this? What is this data telling us? A computer, yes, but what can you tell me anything about the drive time in Los Angeles by looking at those numbers? Nope, it's just a scattered bunch of numbers. So in order for it to mean anything to us, we have to arrange them. We have to put them in some logical order, because from there, that'll help us do our calculations for our everything we're going to look for. The first thing we have to do no, there's more than one sheet. There's five sections in there. So take that whole stack. Yeah. So first thing we have to do is create a frequency table. Remember, we have all this data here. We have to put in some kind of order. To do this, we have to decide on the number of categories. These are called classes. Basically, a class represents how many rows are we going to have? Because we have, if we took these numbers, we'd have 50 of them straight up and down. So we don't want to do that. So we have to put them in a frequency distribution. Okay, so A. We have 50 pieces of data. How many classes do you want? Because what the class is going to do is now we're going to find intervals. We're going to take these numbers and put them in intervals. That way we don't have to put one of each number. That would just be ridiculous. But we're going to talk about those in a second. So hours for this one, let's say we want 7 classes or 7 intervals. Now we need to find the class width. In other words, how big will each of these intervals be? The formula is this way. Class width equals largest number in your data set minus the smallest number in your data set and divide by the number of classes that you want. So that's how we determine the class width. This is really one of the only pieces that you have control over as a researcher. You decide how many classes you're going to have. The more classes you have, the smaller the intervals are going to be. The fewer classes you have, the wider they're going to be. So that's why it's very important to pick a number that makes a lot of sense. So let's look at our data set. The first thing to do is, what are our lowest and highest numbers? Okay, the lowest is 5. What's the highest? No, 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 no. Put that last one back. No, yeah, put it back where you got it from. Because they're in sets already. You should have 5 sets. They're each set of each notes of each section. If it's stapled, that's only 1 set. Yeah, so you see there are 4 more right below where you took that one. The whole stack on top, take it. The whole thing. Yeah, because anything facing the same way you just took it, take that stack. No, negative can be. How many do you have there? Yeah. How many do you have there? Okay, there should be 2 more then. It's set alternating sequence, so it's easier to grab the whole thing. And what's the highest number? 90. And we want the number to be 7. So our class width is going to be 90 minus 5 over 7. There should be, you see the way they're alternating, just take the whole stack on top. The ones pointing the same direction. All of them pointing in that same direction on top. It's, okay, yes, there. So we get 85 over 7. 7 goes into 8 one time with 1 left over. 7 goes into 15 twice with 1 left over. So you have 12 point something like 12.1. You don't want your intervals really to be intervals. I mean, to be decimals. So what we do is we round it up to the next logical number. That makes it easier for us to define sets. So what we're going to do here, the easiest number to deal with would be 15. If we move over to 13, then that's just 14 is also the same thing. It'll make it much more difficult to figure out how you go from set to set. 15 is much. I'll show you why this is an easier number to deal with. So now we create the frequency distribution chart. We have our data. We know how many sets we need. We know what the high and low numbers are. These are our intervals. Okay, if you're trying to follow along on these notepads, don't do that because I'm going all over the place to make it more logical for you to figure out because that's my job is to put the stuff that they don't do in these packets. So don't try to waste your time looking around there. Follow along here because this is not going to be in there. So the intervals. Since our lowest number was 5, what we want is our beginning number to make sure that we incorporate that one. We don't want our lowest number to be the end point. So we're going to start off at 0. And remember, our intervals are 15. What number, if you start at 0, what number is the 15th number? Just think about it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15th number is 14. But what this represents, what this number represents is the lower bound numbers. So this one's going to start at 15. So 0, 15, 15 to 30, 30 to 45, 45 to what number? 60, 60 to 75 to 1, 2, 3, 4, 5, 6, 7. Yes. So you see that there's no overlap. Where this one ends, the next one begins. Because we don't have any decimals. So where is this one going to end? 29, very good. Because the next one starts at 30. This one goes to 44. So it's the same as if we start at 0, we had 14. So 104. That's the 14th number, 15th number. All right. So that's the first step. Now, the reason I said don't look at the try to follow along with that package so far, because we just jumped through a big step. It didn't tell you where this came from. Now, can you tell me how many frequencies we're going to have from our data set? How many numbers between 0 and 14? No, don't do that, because remember, if this is only 50 numbers. So what we're going to do first, we're going to create something called a tally column. What a tally column represents this. I do apologize, yeah, because they needed that room for English department meetings for the district. So they chose that one instead of going in the other empty rooms in the building. So I apologize. So what is tally? So we see in our data set the first three numbers, 18, 25, 45. So 18 is in this one. I put a mark. 25 also there, and 45. You see it? So do that with all 50 of them. And the beautiful thing about this is if you ever get stuck or if you get interrupted, you know exactly where you start off. I already got 3, so I start off in the 4th number. So I did the first 3. Now I'm at 75, 60, 40. 75, 60, 40. So go ahead on your sheets, since you have the data set, go ahead and fill those rest out. I'm going to freeze this. All right, so again, after you have 4 hash marks, the 5th one, put a diagonal so you know. Now we create the frequency column. So we have 5 plus 1 is 6. 5, 10, 15 plus 3 is 18. 5, 10 plus 4 is 14. 5, 5, 1, 1. This is the first step now where we do a checks and balance. If you add up your frequencies, the letter we use for frequency is letter F. In mathematics, I'm going to teach you a symbol also, because remember, mathematics is a language. So this symbol here is called the summa. The sum of. What does sum mean? To do what? Of what? How? Adding them. Sum means the total after you add them all. So this means the summation of F is equal to, there's 10, there's 20, 30. This has to be 50. If it's not 50, if it's more or less, you did something wrong. Why does it have to be 50? Yep, because our sample size is 50. Of course, how many of y'all know how to use Excel? Excel is what you can do this in Excel, but you still have to know what your intervals are going to be. The applications like Excel or any plot stats, all of those have already defined formulas for these. And we'll see in this class that that's not true. The formulas change. Now, in our intervals, these are our classes. These numbers on this side represent the lower class limits. And these numbers on the right are the upper class limits. What do we know about the upper and lower class limits? How far are they apart? Yeah, they're 15 units apart, which is what we wanted our class width to be. And we can also say this is our class boundary. Now, with this type of picture, we can represent something. Have you ever heard the phrase, a picture's worth 1,000 words? When you do a presentation, whenever you finish, you graduate, get a job, and you have to do a presentation for your boss, they don't want to see a bunch of numbers because you're looking at hundreds, maybe thousands of numbers. They don't want to see those. That's going to give them headaches. So what they want to see a picture, and the picture that'll tell me a lot of the story. So the first graph we can use is a frequency distribution chart. What do you think's on a distribution chart? What do you think is going to represent? This is the frequency, and this is the class. What it's going to do is it's going to take our data that we have there, we put it in a frequency distribution chart. Now we're going to make it, it's not a graph, it's a graph. Two, four, 6, 8, 10, 12. Bless you. Now, this is our frequencies. What numbers do we use for our classes? Remember, our classes are intervals. I don't want an interval there. I want one number because I got to take this X value and match it to a Y value. It's a point. So how do I get an X value? Which one? And so what number is that going to find for us? But I only want one number. What number is going to represent that interval? No. What number is going to represent the next one? Why 6? You're close, but it's not 6. That's the frequency of that interval. If you have an interval, the number in the middle represents that interval. The number in the middle. What number is in the middle of 0 to 14? How'd you get 7? Well, but what about the next one? What's the number in the middle here? Yes, it's easy when 0 is one of them. But you're right. It's half of 14. But what is going to be here? What we want is the class midpoint. Take the lower class, add it to the upper class, and divide by 2. So you're taking the average. You find the number in the middle is finding the average. 0 plus 14 divided by 2 is 7. 15 plus 29 is? Everybody's taking off their shoes and using toes. 44 divided by 2? 30 plus 44? Divided by 2? And yes, we keep on going that way. I'm going to show you another shortcut. Remember our class width was how much? 15. How much is it between 7 and 22? 22 to 37. So you add 15. So the next one's going to be what? 37 plus 15 is 52 plus 17, or plus 15, I mean. And you keep on going. 67 plus 15. No, we don't need the next one. There's no next one. Because 97 is in the between 90 and 104. We don't have anything higher than 104. 1, 2, 3, 4, 5, 6. We have 7 numbers because we have 7 classes. All right. So how many were in the first one? There were 6. So we put a dot there. In the next set, we had 18. In the next set, we had 14. Then 5. Then 5. Then 1. Then 1. Just connect them with a line. Some people also call this a line graph. So far, so good? There's another topic we talk about. It's called relative frequency, or we call it a percentage frequency. Distribution. Why is it called a distribution? Because we want to see how the data is distributed on our entire data set, on our graph. So that's why all these are distributions. For example, 2, as you can see on your sheet, we have another one. The cause of fatal aircraft accidents. This is table 2, 3. Causes of fatal plane crashes. Here's our cause. Pilot error. Mechanical. Sabotage. Weather. And other. and it's given us our frequencies. The relative frequency the reason it's called relative is because what we're doing here is we're looking at this frequency, how it relates to all the other frequencies. So in other words, how is pilot error associated with all the other causes of airplane accidents in this case? Formula. So RF is equal to the class frequency total size of data. This is the N number. So what we have is this, is the frequency of the class divided by N. So in our example here, the airplane accident one, what's our N? What's our N? Add up all the frequencies. Remember, the formula for N is the summation of all your frequencies. Mm-hmm. 104. Yes. So the relative frequency of the first one is 640 divided by 1104. The next one is 195 divided by 1104. 95 divided by 1104. 63 divided by 1104. And 111 divided by 1104. So what's the first one? So what'd you get for the first one? 640 divided by 1104. I know y'all have your cell phones out. Zero point 58. Thank you. Let me see. Zero point 18. Let's see. So is everybody familiar with the rounding rules of math? We're always going to round in until everybody noted to 2 decimal places. So we look at the third decimal number. If it's greater than 4, then we drop everything and add 1 to this number. So if it's less than 5, it's between 0 and 4, we just drop everything after it. That's the rounding rules. So it's 0.17. The next one is 95 divided by 1104. Whoops. Four. 0.09. Six three divided by 1104. 0.60. Good morning. We were kicked out of our other room because they needed it for a meeting. The last one is 0.10. No, I made a mistake there. 60. No, please. Thank you. 63 divided by 1104 is 0.06. So that's the relative frequency. Not too impressive, is it? Decimals aren't really that friendly to us. So what can we do with decimals to make them represent more stuff? Go ahead. Turn them into percent. Exactly. How do we turn these into percent? Yeah, multiply by 100, which makes it 58%, 18%, 9%, 6%, and 10%. That's called the percentage frequency or percent frequency. And that's what we just, since they're so close together, we don't use relative frequency for anything else. So instead of calling it the percent, that's what we always refer to the relative frequency, because the relative frequency of the pilot error is 58%. What does that number tell us? What does 58% tell us? It tells us that 58% of the time, anytime a plane crashes, 58% of the time it's pilot error. nine times out of 100, 9% of the times, it's sabotage. 6% of the time it's weather, 10% of the time it's something else. Like an animal, a bird hitting a flying animal when you're flying. Or when trying to land, a bird or something gets sucked up in your engines and it kills the engine. So those are relative frequencies. We get those from the frequency distribution. So let's do a relative frequency for our original data set. Where's it? There's, so for our frequency table here, let's create a relative frequency column in percents. So we have the class, the frequency, and the relative frequency. So all these classes. Remember, we're supposed to have 7 rows. From 0 to 14, 15 to 29, 30 to 44, 45 to 59, 60 to 74, 75 to 89, and 90 to 104. Our frequencies were 6, 18, 14, 5, 5, 1, 1. Remember, first thing we did is after we create frequency, the summation of all of our frequencies is our n, which should be 50. We have to know this number. Why? Why do we have to know the n number? Exactly. To find the relative frequency, we need the frequency divided by n times 100. That's the formula for the relative frequency. So we have 6 divided by 50 times 100. That'll give us some percent. So we have 6 divided by 50 equals 12%. So take 0.12 times 100. In other words, all that means is move the decimal 2 to the right. So whenever you do a conversion, 0.12 to percent is move it 2 to the right, and it becomes 12%. The relative is the frequency of that class divided by n, which is the summation of all that class, all the classes, times 100. So what we had to do is we had to first find the number of elements in each class, each interval. So how many numbers in our data set are between 0 and 14? How many of them are between 15 and 29? Once we find all those sets, and those frequencies, that's our F. Each one of those numbers, the 6, the 18, the 14, the frequencies, those are our F numbers. So we take F divided by N times 100, and that gives us our percentages. N is what? And 50. Yeah, it's in our data set. Our first data set we started off with is 50. There are 50 numbers in our data set. So 6 divided by 50 is 0.12 times 100 is 12. Then we have 36%. Then we have 0.28, which is 28%, 10%, 10%, 2%, and 2%. We always have to have a checks and balance. We added up our frequencies to find our N, to make sure we had the same number of frequencies that we have number of data. What do we do? What happens if we add up all the frequencies, relative frequencies? Should we what? It's what? It should equal 100%. That was a good guess, though. But no, it's not 50, it's 100%. Remember, these are now in percents. Okay, now will it always equal 100%? No. Why? Because remember, we took some numbers like 0.1875 and made it to 19%. We rounded off. So if as long as it's close to 100, that's called round off error, and we're happy. But if it's not, if it's far away, if it was like, if you ended up with 92 or 93, that's too far. Or if you ended up with 103 or 104, that's too far from 100. You want it to be pretty close, no more than a point and a half. Any questions so far? So looking at the frequency tells us how the data is distributed throughout, how they're each related to each other. The percentages, what do you think the relative frequencies are going to help us do? The relative frequency helps us determine how much of it is taken up of this event. So there's 36% of the data falls between 15 and 29. 10% of the data falls between 60 and 74. Now, what does percent mean? What it really means is this. If I had to pick a number, there's a 10% chance that I'll pick it in this interval or in this interval. Or I have a 36% chance of this happening. Another good thing about these, remember the graphs of relative frequencies are similar to those of frequency. They're the line charts. You can overlap 2 or 3 pieces of information and compare them that way. On page 6 of your notes, we see this. We can compare the daily commute and times in New York and Boise, Indiana, in minutes. So what we would do is we would take these intervals. Remember so look for the packet that says chapter 2, section 1. Look at on page 6. I think it's page 6. Page 5. I should put numbers on these. It's not there? All right. Oh, well, you'll have, this is the information. It's not there? Nowhere in your packet? Really? So we're missing pages? Ugh. Stupid printer. Because you notice half of them may have the first page is not stapled to this whole packet. So, okay, I will send those to you so you'll have the entire packet. I apologize. Wow, that's too weird. It just decides to only do odd number pages. That's weird. Anyway, here's the data we should have in our packets. I do apologize. Right now, again, when you just look at numbers like this, it means nothing to us. So when we look at this as 8.8% of the people commute for between 0 and 14 minutes to go to work in New York, as opposed to 30 minutes in Indiana, in Boise. What does that tell you? Or 45% between 15 and 29 minutes in Boise, 20% in New York. What it tells us is this. I said, look at the first interval between 0 and 14 minutes. New York is 8.8% of the people commute that time, as opposed to 30% of the people in Boise. In New York, there's no such thing really of a short commute. The data is further skewed where it goes to 30 to anywhere between 15 and 60 minutes is your average commute. As opposed to Boise, everything happens in the first 30 minutes. So if you're looking to a place to live, to move that, if you don't like a lot of people, this is the kind of data you should be looking at. What is the average commute time to go to work? What this tells us is, okay, there aren't many people, or people live closer to where they work. New York, we know it's crowded, so it takes a long time to get anywhere. LA would be even worse. LA would be 3 or 4 hours to get to work. Now, we have another set type, is called cumulative frequency. A cumulative frequency distribution. What does cumulative mean? If your final exam is cumulative, what does that mean? Total of everything. Yeah, it's everything. So let's look back at our data, because we have our class, we have our frequency. Now we're going to get a cumulative frequency. So the first class is 0 to 14, it's 6. 15 to 29, it's 18. 30 to 44, it's 14. 45 to 59, it's 5. 60 to 74, it's also 5. 75 to 89 is 1. 90 to 104 is also 1. And for us to know if that's the appropriate frequency chart, we have to add up all our frequencies to get 50. The cumulative frequency does that for us. The cumulative frequency, another name for it, is a running total. So in the first one, we start at 6. We have 6. Now in the next one, it's a running total. So we have these 6 plus these 18, which is what? That's 24. For the next one, we have 20, these 24 we start off with. Now we had 14 more. We have 38. These 38, we pick up 5 more. We get 43. These 43 pick up 5 more. These 48 pick up 1 more. And these 49 pick up 1 more. So the cumulative frequency is just that. It's a running total of each class. As we go down further, we get the same, we get the class number of how many pieces of data are up to this point. Now, the last topic of this section deals with something called normal distribution. Normal distribution. What normal distribution tells us is if the data is evenly spread out. By what I mean by evenly, you ever heard of the bell curve? That's what it means. The bell curve represents the normal distribution. If we were to look at our frequencies, what we would want is a shape something similar to the bell. Remember this shape because it's gonna be with us for the rest of the semester. The bell curve. It's an upside down curve, which means that the middle of it, it's symmetric. The left side is equal to the right side. So as they're distributing, they'll be the same. And right now, we're not going to deal with determining whether it's normal other than by the graph. If I graph our function, our data set, and it looks like this when we do the numbers, then we can see is it normally distributed. Is it normally distributed? No, it's what we called, it's positively skewed, right? But we'll talk about that in the next section. Let's look at an example here. Example 4. Frequencies of last digits sometimes reveal how the data were collected or measured. Frequency of the last digit. Think about what that means. Why would the last digit be important? I'll show you. Let's look at this table, this next one. If we have a data set where the last digit The last digit can be either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Has to be one of those numbers. The frequency of the first one is 455, 0, 461, 0, 479, 0, 425, 0, 399, and also last one 0. So why would that be? What would that tell us? What do you notice about that data set? Where are the zeros? And what kind of numbers? Yeah. So that means the data collected are only even integers. All the odd numbers don't exist. When would that work? When does something like that happen? Medicine is the first one you come up with. Pulse rates. How long do you take the pulse rate test of a patient? 1 minute. So in other words, it's going to be well-rounded that way. And if you take a minute and divide it in half, you get 30. It's always going to be an even number. All the odd numbers don't exist. So the data we have here for this set is, we know that we have a data set of something that is always rounded up to even numbers, or only use even numbers. Pulse rate's the first thing that comes to mind. When you hear the word gap, what does that mean? A space, a hole. Here's just here. The presence of gaps can suggest that the data are from 2 or more different populations. Why would it suggest that? Are all populations, do they all have the same characteristics? Nope. For our example here, our table 2-9, pennies. The weight of pennies. Here's the weight, and here's the frequency. So the first one is between 2.40 and 2.49. There are 18 of them. 2.50, 2.59. There are 19 of them. 2.60, 2.69. There are none of them. 2.70 to 2.79. There are 0 of them. 2.80 to 2.89. There are also 0. 2.90 to 2.99. We get 0. Or no, we get 2. And the last two, 3.0 to 3.09. We got 25 of them. And 3.1 to 3.19. We get 8. First off, does everybody remember what a penny is? You'd be surprised. A lot of people don't use pennies or collect them, or if they get them, they just toss them on the floor. There are some places, military bases around the world, don't use pennies anymore. They round everything up to the nickel. It makes it much easier to take care of that way. So why would you think this is happening? Why would the weights of these pennies be different? Penny is a penny, isn't it? Very good. That's exactly right. They were made at different times. Why would that matter? What happened in different times? Fabulous. Yes. Because the material they use, you would think that pennies made up of what? Just copper. So pennies before 1983 had mostly copper and then 5% zinc. After 1983, they were 97.5% zinc and the rest copper. So it was before 90, it was 95% copper. And then afterwards, it was only what? 97. So it's 2.5% copper. Do copper and zinc weigh the same? No. So which ones do you think weigh more? Copper. So yes, so if you want to know what you're dealing with, the weight is a perfect weight. Do you ever hear the story of where the word eureka came from? Oh, thousands of years ago, hundreds of years ago, in Greece or some one of those Mediterranean countries. The king asked somebody to make them a special crown of gold. And the guy built it. But he didn't use pure gold because he figured that the king gave him all this gold. He told him to use it. So he said, no, I'm going to keep most of it myself. I'm just going to make something gold plated. King will never know. So Archimedes, I think it's Archimedes. And the king asked him, he was smart guy, said, is this pure gold? I don't know. I don't want to destroy it because it's a beautiful crown. So Archimedes, I believe it was him, but he went to take a bath. The bathtub was full. And he got in, and what happens when you get in a bathtub? If it's full to the top? The water moves out. That's called displacement. So what he thought was different objects, different weighted objects displace different amounts of water. So he took this crown, weighed it, and took the same amount of gold and put them both in the water. Guess what happened? They weren't the same. So the king knew that he was gypped. So off goes the other guy's head. And he gets his gold back. But that's the kind of stuff is, if you want to compare something, look at the weight of it. Okay, that's the end of that section.